Okay, so I left off with making the point that a lot of local scale phenomena are missed with climate models. And I want to transition now to say that also there are some really very core scale things that may not be missed, but they're pretty damn difficult. And so this is a picture from an introductory biology textbook for use for 2B, and it's showing these Hadley cells. And so if you haven't heard about Hadley cells, I'll just give a quick rundown for them. If not, you might skip ahead a minute or so. But basically, at the equator, there is the strongest area of upwelling, or sorry, uplift of tropical air. And as it's rising up, it is dropping its moisture, making the tropics very wet. But it is not rising into a vacuum. It's displacing air as it rises. It's displacing air that went up previous to that. And this is because this is this maximum area of solar radiation. That displaced air can move to the north and to the south, and that it slowly descends. As it descends, this dry air warms. As you know, and the Chinook winds and things are things are winds that are moving down the mountain, and as they move down in elevation, they're condensing, and that condensing increases the energy. It warms it up, and warmer air has an increased capacity to hold moisture. And so, same thing is happening here. Air is sinking; it's becoming more concentrated. It's warming up, and it has increased capacity to hold water. And so, what you end up with are the desert biomes of the world at about 30 degrees latitude. And we can measure this from space. Here's a vertical air velocity in July where blue is rising air. And you can just see that air moving up and the red air, the sinking air, north and south of that from those Hadley cells. And you can also see it in cloud cover. This is what's known as the intertropical convergence zone. It may swing a little to the north or a little to the south of the equator with seasons as the Earth tilts. But you can see that you get increased cloud cover at the equator. And that this is also, because the Earth is spinning, responsible for these trade winds. So the Earth is spinning around as the arrow shows in that diagram, and that the air sinking back down is coming out and filling in, because again the air doesn't leave a vacuum behind. So the air that's rising up and pushing air, displacing air at higher elevation, is also pulling air in, and it's pulling in air in the counter direction of the Earth, spinning of the Earth, which gives rise to the trade winds, because you could sail from east in Europe to west in the Americas using them. And that this then results in these global patterns of precipitation, where you have the Sahara just north, around 30 degrees north of the equator, all the way up to the Gobi, why Australia and South Africa and parts of Chile are some of the driest parts of the world, over down there in Namibia. That the global biomes follow these kinds of patterns. There's of course latitudinal gradients with boreal forests and tundra far north, but you can see north to south patterns, particularly in the Americas where you have mountains, but you also have these desert and dry areas. Well, overlaying on all of that is the jet stream. So there's a polar jet stream and a subtropical jet stream, and it's been likened to an egg cracked on the top of the Earth, how it dips down and comes back up again, and these things are responsible for when it gets really cold down in Dallas and you have those ice storms. That's the jet stream just blowing down through the center of the North American continent and bringing a lot of cold air with it. And that when we get these what they call pineapple expresses, that's often the subtropical jet stream just ripping northward up into California, bringing a lot of moisture with it. And so down the lower right, you see the Hadley cell, and then what the northern one, which is the next period north, which is these Ferrel cells, and they show that these jet streams are actually tucked right around the edges of these contact points between these different cells, because there's these different cells. The Hadley cell is not the only cell going on there. That north, there's another thing called a Ferrel cell that is turning the opposite direction. So global circulation models try and capture all these things and put them in, but it becomes very tricky, because what we get in California is that we're going to have a strengthening of the polar jet stream, and as a consequence, we'll have cooler, moisture air coming down out of the north. And the global models predict that you're going to increase the Hadley cells, which is going to increase that dry desert-like air from the south. And so we're sitting at this cusp where moisture is very important to most of our systems, and about the northern half of this, or 2/3 of the state maybe even, are predicted to get wetter, and the southern third to half drier based on different models, and that this makes prediction here very difficult. So this is a little bit of a complex diagram that you might pause and ponder for a minute. But if you take a bunch of the CMIP3 and the CMIP5, these are from the 5th and 4th assessments respectively, and ask what is the expected amount of temperature change in minimum air temperatures, that's across the x-axis, and percentage change in precipitation, that's across the y-axis. And if you take all the cells in, say, California, this is for California, what's the maximum and minimum amount of projected change in these models that the models predict? And so this green diamond that's far off to the left above the axis is a particular climate change models, and there's dozens of them. And with a particular emission scenario, the RCP 2.6 in this case. And you see that this predicts anywhere between a 35% and a 15% increase in precipitation, and anywhere between 3/4 and 1 1/4 degrees by the end of the century. And then that middle point in there, the red diamond, is the ensemble mean. And the ensemble mean for the entire state of California suggests relatively little climate change. But even a model like the PCM-A2, kind of right in the middle there, it's a warmer and wetter model. It's not wetter everywhere in California, and it's not the wettest. It's not necessarily rank order wettest everywhere in California. So climate modelers who want to look at ecological impacts of climate tend to do one of two or three things. They pick a model that they like, that's a bad idea. Two, they take all the models that are possible and they make an ensemble mean. This also seems like a bad idea. Or they do all the models and take some representative ones that represent the warmest and driest, or less, or the coolest and wettest kinds of modeled futures. Like, so using the MIROC RCP 8.5 down in the lower right is a fairly warm water model, not the warmest, but it is the driest. And so that kind of model would be a more extreme prediction than others. But then generally we then tend to model things based on means, and so those are the mean temperature changes in minimum air temperatures, and so it's very common for people to do a species distribution model and predict the response of a species based on annual precipitation or minimum air temperatures during various different seasons. And I'm going to make the point in a couple of minutes that that's a pretty rough thing to do. So from this we get these global predictions of temperature and precipitation. I'm not going to spend any time on these. This is straight out of the IPCC framework. But talk a little bit more about this. This is what El Nino looks like on the top and La Nina down the bottom. If you look at sea surface temperature anomalies, and NOAA plots this daily, it looks a lot like this right now. The surface temperatures around the equator get very warm, and that as a consequence we strengthen those tropical jet streams and get a lot of moisture coming up out of the tropics. And it's supposed to make us wet, particularly Southern California. Now, so far this year, one could argue that we haven't really seen any El Nino effects because Southern California hasn't been particularly wet, and most of our storms have been coming in cold and leaving a lot of snow, which is, of course, good for us, but it's not what you expect necessarily in an El Nino year. So these extreme events may be incredibly important for ecological impacts. Just a little bit more about El Nino. This is recent El Ninos over the last, this is a couple of weeks ago now, but here it is from December 13th to January, the sea surface temperature off of our coast. And this is just to say that over the last few years, we've had this thing that they were calling the blob, which is a bunch of warm water up around the Gulf of Alaska up there, and this ridiculously resilient ridge, which has been bouncing these storms around us and not getting them. And this is from a couple of weeks ago, January 10th, now almost a month ago. But we're more or less tracking along that blue curve there. If this is the water year, we expect on average to be on that blue curve for these 8 stations in Northern California, and that drives a lot of the water and reservoirs and things. So it's a good one to look at. Pink and green are the wettest years on record. Brown is last year, and you can see that really up through early or around the turn for first of the year, we weren't very much different than last year. But then last year it just shut off, and this year we've done a little better. We're up around 30 on the y-axis now. But if you look at the longer range forecast, it's sort of shut off for the time being. So we're in our January dry period, which is not at all unusual. Okay, so using those mean temperatures, there's myriad studies that suggest that climate vulnerability is going to be it's going to be a disaster for biodiversity. That upwards of 30% of species may be at risk of elevated risk of extinction. But bear in mind that that's based on looking at those mean climatic values, and I think that that's a pretty weak way to model. And I'll talk about why I think so in just a minute. So, of course, this leads to conservationists and thinking about what path do we follow, what should we do, what are our strategies. This is a paper by Maudsley. They'll be talking about this in class, so I'm not going to go into this in any detail at the present time. But the point that I made in this webinar was that we're now in a position where land is fairly contested, and California is about half public lands and half private lands. Well, it's not a lot of underutilized land out there. I mean, the ranching is in trouble, but we have a lot of cropland, a lot of urban land that there's high demand on those habitats, and so it's not as if we can set aside a lot more land for protection as a strategy for conservation. And one of the problems that people worry about is the lack of ability of species to move fast enough to keep pace with climate change. And so people have suggested this idea of assisted migration, the intentional act of moving species into locations not considered within their historic distribution for the purpose of conserving biological diversity. And this comes to the fore in places like Joshua Tree National Park, where I'm not going to go into it in great detail, but the green areas represent areas where Joshua Tree is projected to thrive at the end of the century, but isn't currently. Red are places where it is currently and expected not to be in the future. And orange, you can barely see any orange, look like places where they could naturally migrate to. And yellow is where they are currently, yellow is where they could naturally migrate to, and orange is where they currently are and are projected to be in the future. And so this brings to things like Joshua Tree National Park into focus of saying, well, what would it be without Joshua trees? What should you be managing for? And perhaps I've mentioned in class that the Leopold Commission issued a report in the 1960s that basically suggested that parks are to be managed to maintain pristine pre-European visages of these ecosystems. And this was the Science Advisory Committee for the National Park System revisiting this and saying, well, if that's not possible because of climate change, we're not looking backwards. What is the mandate that we have for managing things? Is it and they came up with ecological integrity, cultural and historic authenticity. So it needs to be authentic, but not necessarily exactly what the history was, and then provide transformative experiences. And so that's sort of the marching orders. This is nothing formal, but this is kind of the direction that the National Park Service is going. Oh, good Lord. This is going to take me 3 of these dang YouTubes, although the third one, I promise, it will be short. Okay, I'm going to stop this one now.